let's say that we're interested in a particular variable, and let's say that variable is IQ scores. And let's say that we measure a whole bunch of people's IQ scores, and we go into our data set, and we want to know an IQ score between 100 and 101, for example. How frequently does that occur in the data set? And let's say that we plot that as a histogram, and that's going to be plotted, let's say, like this. So there's going to be a large number of people who have an IQ score between 100 and 101. And then let's say that we do that for all IQ scores. And it turns out that we'll see a distribution that looks like this. Simply in the other direction. So we're plotting a histogram that represents this distribution of IQ scores. And you happen to see that if you connected a smooth curve to this, so again, you would be trying to construct a frequency polygon here and labeling the midpoints of each of these heights. And then you connect each of these midpoints with a smooth curve. And you'll see that you have something like this. Simply in the other direction. So what this picture is supposed to be is it's supposed to be a graph that is symmetric on both sides. So the center here would be like a mirror image where both sides were symmetric, were similar to the other side. And this is what we call a bell curve. So in this example of IQ scores, there's some IQ that is represented the most often in the data set, in the population. And that happens to be an IQ score of 100. So as you move away from an IQ score of 100 in either direction, you're going to get less and less representation. So for example, somebody out here that has an IQ score of 180, that's going to be very rare, where very few people will have that. And likewise, over on the other side, an IQ score that's low, like 70, will be rare as well, and so forth. So this is an example of a bell curve. There's some variables in real life that are distributed as bell curves, such as IQ scores. So what other variables do you think in real life might be distributed as bell curves? Yeah.
Age, maybe? Test grades.
Yeah, test grades. So let's talk more about that. So the short answer is maybe, maybe not. So it turns out that if I gave you a test that was really easy, it was so easy that almost the whole class got 100 on it. Like, I asked you what your name is, for example. So, if it's so easy that at these high scores, at the 90s and 100s, you're going to get a lot of representation there. And at the 90s, 90 and 100, a lot of people would get. 80s, maybe there's a few people who get 80s, and then the low grades, nobody get those grades because the test is so easy. So if you connected this with a smooth curve, you might see something that looks like this. So this example would not be a bell curve because it's not symmetric on both sides. You don't have a center value that peaks and then it tapers off on both sides where it ends up being symmetric. So this would be a bell curve. This example would not be because the test is so easy. So normally, you don't have tests that are too easy or too hard. So most of the time, yes, tests, especially standardized tests, you do have distributions that are bell curves for standardized tests, like SAT, ACT, FCAT, and so forth. So what other examples do you think are bell curves?
I was gonna say like the average age.
Okay, so average age, and let's say average age in the country. Short answer is maybe, maybe not. So we only really know if we have the data set in front of us. So if we have every single person's age in front of us, and then we constructed a histogram, and then we saw whether that histogram was in the shape of a bell curve, then yes, it would be a bell curve. But right now, without seeing the data, maybe, maybe not. Good, yeah.
Like height and weight.
Okay, excellent. So it turns out that those are examples of perfect bell curves, where you have height and weight. There is some height that the most number of people have, and as you move away from that height in either direction, it tapers off and it's symmetric on both sides. Okay, and the same thing for weight. So let's do an example together. What do you guys think about income distribution in the US? So again, it depends on the data set. You don't know for absolute certainty unless you have all the data in front of you and then you plot the histogram. But without even having the data in front of us, let's just think about our collective experience together. And if income was actually a bell curve, then there would be some income that represents the average where the most number of people have that income. So what would that be approximately?
Isn't it like 60,000 for the US right now?
Okay, so let's say 60,000. So 60K, we're gonna have a bar with a certain height indicating how many people have that particular income. So if the distribution is the bell curve, then we said that it needs to taper off as you move away from this peak, and also it needs to be symmetric on both sides. So let's imagine that we have, let's say we move 50,000 on both sides, where over here we have 10K, and over here we have 110K. So the question is the height of the bar the same for both? If it is, then we have a chance of this being a bell curve. But if it's not, then this is not symmetric, it's not a bell curve. So do you think that the height of the bar or the number of people who make 10K a year, is that gonna be the same as the number of people who make 110K? Yeah, so no. So I would venture to say, without even looking at the data, that there's more people who make 10K than 110K. So you're probably gonna get something like this. And so this is a very skewed graph, so it'll probably look something like this if you're gonna plot it. So this would end up not being a bell curve. Any questions? Okay, so this is just an introduction to bell curves, which is what the general shape of the distribution of a bell curve looks like. But later on in the semester, we'll talk about bell curves in excruciating detail. And we'll talk about it a lot more. Okay. So that's chapter 2. That's basically visualizing our data set with tables and graphs. And we talked about the specific types of graphs. And so now let's move on to chapter 3.